This is chapter 17. We're going to talk about the traumatic brain injury in the guide text. Now, this is not a replacement for reading your text. This is just a supplement. So make sure you do read your text. There's a small section in this chapter on spinal cord injury and our management of the spinal cord injury. This is becoming antiquated information. Turns out that the treatments that they had for spinal cord injury are falling by the wayside, so we're not going to address those here. When there's blunt trauma that strikes the brain, we have a wave of energy across the brain, that counter-coup type of action. This is what causes that primary brain injury. We can't do anything about this. However, what we're going to be concerned about is something that's much more deadly. That wave of energy through the brain makes the brain jiggle inside of the cranium, causing counter-coup injuries. This is what triggers the secondary brain injury. That causes swelling. The brain's response to everything is to swell. And that's going to trigger the cascading events that's going to cause the secondary brain injury. Now, this is what we are hopefully going to be able to manage.
The problem with the swelling brain is the fact that that brain is inside an enclosed container, the cranial vault. Matter of fact, the brain occupies about 80% of the space inside of the cranial vault. The remaining 20% is occupied by things such as cerebrospinal fluid, the blood that's in the arteries, and then the blood that's in the veins. The body has ways of compensating. One of the compensatory mechanisms that the body has for increased intracranial pressure is initially it will move a lot of the cerebrospinal fluid out of the cranial space. Additionally, it's going to compress on the arteries and compress on the veins. But that's only going to go so far. You can't decrease or eliminate the amount of blood coming into the brain. That would be death. And additionally, you can't not have the blood return to the venous system. So they're only going to give so far. Once these compensatory mechanisms start to fail, the result is we're going to have an absolute increase in pressure inside that cranial vault.
Once we start this period of increased intracranial pressure, things are going to start to decompensate quickly. Increasing intracranial pressure puts pressure on the brain tissue. It increases the cerebral perfusion pressure. In order to perfuse the brain with an increased cerebral perfusion pressure, we have to increase the blood pressure. Increasing the blood pressure means that we increase the volume of the brain inside the skull. Increasing the volume of the brain inside the skull increases the intracranial pressure, requiring an increased blood pressure to compensate for the increased cerebral perfusion pressure. And it turns into a rapidly declining process in which things just aren't going to go well. This CAT scan of an epidural bleed is an example of that. Here we have a mass of blood from traumatic injury. We have a bleeding occurring inside the epidural space, pushing on the brain. You can see here that we have a collapsed right ventricle. We also have the midline of the brain shifting towards the left. This is saying that there's a massive amount of pressure pushing the brain to one side of the head. The result here is we've removed as much cerebrospinal fluid as the brain's going to accommodate. We still have to have some arterial pressure, so there's still going to be some volume in the arteries. The veins are collapsing, but you still have to get blood out of the brain through the venous system. So all the accommodations have been made. There's no more compensatory mechanisms that are capable of happening. So this patient is going to have an increased intracranial pressure as a result of this bleed. In all things, the management of the patient is going to be directed at managing the secondary brain injury. How to reduce the intercerebral swelling that's going on. That intercerebral swelling is the driver that's causing that cascade of events that's taking the patient down an ever declining cycle. If we can reduce that brain swelling, maybe we can break this chain of events. In hospital, in the ICU, they're talking about physically removing portions of the skull, allowing the brain to swell inside the cranium. They may drill burr holes in the skull to let off intracranial pressures. They may do medically induced medical comas to try to let the patient heal with lowered brain activities. There's talk about hypothermic managements for the patient. All of those are way above our pay grade. How do we manage the patient? Well, we're going to do our best to contribute to the breaking of this ever declining cycle. The two things that we can do first is to manage hypoxia. This patient has respiratory problems. They have ventilatory problems because of the regulatory centers of the brain being compressed. So the ventilations that they're doing is going to be retaining a lot of carbon dioxide. And that's bad because carbon dioxide is a vasodilator. If we dilate all the vessels inside the brain, the volume of the brain itself is going to increase. So oxygen's good. But here, oxygen is also good because it replaces carbon dioxide, which is bad. We're going to remove carbon dioxide by ventilating the patient. Our rule of thumb is 12 to 20 ventilations per minute. And if we do it with supplemental oxygen, 100% supplemental oxygen, we probably have the patient in the right range for managing any hypoxia. The second goal is to not let the patient become hypotensive. We know that cerebral perfusion pressure is elevated. Blood pressure has to be elevated as well. If blood pressure starts to fall for any reason, the result is we're going to have cerebral starvation. Without the ability to push blood into that increased pressure in the cranium, the brain tissue is going to die off very quickly. So what pressure do we want to keep the patient at? Well, we can't know that. We have no idea. We can't measure cerebral perfusion pressure and apply a formula. So the only one thing that we can do is to make sure they don't go hypotensive. Don't let them go hypotensive. Make sure that for whatever reason, the blood pressure does not drop below 90. I can't tell you what pressure is perfusing this patient's brain, but I can tell you that when they're in shock and their blood pressure is below 90, it's not adequate. So those are our two goals in managing this ever downward spiral of badness. One of the treatments they can do in hospital is going to be administering mannitol. We talk about mannitol, it's one of our drugs, but we don't administer it pre-hospital, and there's a logistical reason for that. Mannitol is a non-sweet, high molecular weight, multi-carboned sugar. The purpose of mannitol is to get it into the vascular system because you have this heavy hypertonic sugar in the vascular system. It's going to draw fluid off of the cerebral space, the interstitial spaces that's responsible for edema. So this will reduce the cerebral swelling. That's great, but the problem with mannitol and the sugar is it can't come into physical contact with the nerve tissue itself. It's kind of like holy water on a vampire. It just kills it. If we have extravasation and the mannitol can actually physically leak out into the brain space, it can cause cerebral necrosis. So they have to perform a CAT scan to assure that there is no intercerebral bleeds that are occurring before they can give mannitol. If there are no intercerebral bleeds and it's just a cerebral edema and a swelling from blunt force trauma, this is a viable alternative to manage the patient. The concept is the same for 3% saline solution. 3% saline solution is much more salty than is your standard 0.9% saline solution. This is hypertonic. By administering this saline solution into the vascular space, it's going to draw off the fluids from the cerebral edema, drawing it into the vascular space and letting that fluid excrete out through the urine. This is an alternative, and they've advocated this pre-hospital. One of the things that they have to be very cautious about this is it's going to pull fluid out of all of the spaces, all the interstitial spaces. So not only is it going to reduce cerebral edema, but it's going to pull fluid in from body wide. The result is the patient's blood pressure is going to go up because your blood volume is going to increase. You're going to be salty, but you're going to be hypertensive. But that is another option that they have to reduce the cerebral edema. Both the mannitol and the hypertonic solution currently are in hospital management. So in summary, what do we have that we can do for our patient? We can keep them from becoming hypovolemic. We can keep them from becoming hypoxic. That means blood pressure has to stay at least over 90. At what point in time is the cerebral perfusion pressure above the mean arterial pressure? Well, we can't know that. We have no idea. But we do know what hypovolemia looks like. So at a minimum, do not let your patient become hypovolemic. Additionally, the patient who has traumatic brain injury is having respiratory problems. Respirations are not being regulated. They're probably going to go into periods of hypoventilation. We can't allow this. We have to ventilate our patient. The rule of thumb is we will need to ventilate a patient normal respiratory rates, 12 to 20. But if we do it on 100% oxygen, we're going to be oxygenating the patient adequately to avoid hypoxia. Intubation, oxygenation is the way to avoid that pitfall of hypoxia. By not letting the patient get hypotensive, we're going to keep the brain perfused with blood supply. Pre-hospital, this is the best thing we can do. Oh yes, by the way, make car go fast.